Hello. Throughout this project, our task has been to investigate chaos and the Lorenz equations, with a particular focus on the sensitivity to initial conditions and model parameters. In this presentation, we will tell you about how the equations were formed, how they are used in today's society, and we will provide some diagrams to help you understand these ideas.
So, in our everyday lives, the word chaos, we use it to describe complete disorder. However, in mathematics, we use the word chaos to describe unpredictability. Chaos is the branch of mathematics that focuses on the behaviour of dynamical systems which are highly sensitive to initial conditions. In other words, the study of chaos is observing systems that experience change and produce wildly different outcomes depending on where they started and the conditions that they were in. A simple example of chaos is the butterfly effect. The butterfly effect says that every movement, no matter how small, has the ability to cause large effects, or equally have no effect at all. This gives the theoretical example that the flap of a butterfly's wing has the ability to cause a tornado on the other side of the world, or equally have no effect at all.
The Lorenz attractors within chaos theory were first studied by the meteorologist and mathematician Edward Lorenz in the 1960s. Lorenz wanted to formulate a simple model to explain the unpredictability of weather. In particular, why weather forecasts with very similar starting points have such different outcomes. Lorenz used a simplified model of convection in the Earth's atmosphere to obtain his equations. However, the Lorenz equations we use today were discovered by accident. Because he was constructing his mathematical model in the 1960s, he had to use a printout to see his results from the computer. When examining a particular sequence of results at greater length, he entered the numbers for the initial conditions from an earlier printout. When he returned an hour later, he found that the new values diverged rapidly from the values on the previous printout, so much so that all resemblance between the two had disappeared. Lorenz realized that a tiny difference in initial conditions had caused this divergence. 6 decimal places were stored on the computer, whereas only 3 were on the printout. This tiny difference would have been regarded by most as having no practical effect on the data. Lorenz, however, saw that the extra 3 decimal places modelled a sensitivity to initial conditions and caused the values to branch off from each other. Lorenz also realised that as time goes on, the 2 values would branch off more and more. The discovery of the Lorenz attractors and chaos in the weather has led to vast improvements in weather forecasting. In particular, something called an Samel Forecast, which is a technique that recognises that any and all measurements for forecasting weather are mathematically imperfect. And so meteorologists run multiple simulations, each starting from slightly different conditions. They take the features from each of these simulations to form a more reliable consensus forecast. Unfortunately, due to the divergence over time, these results become less accurate over time, and so are only used for short-term predictions.
The Lorenz equations are 3 differential equations, as you can see on the screen. They contain 3 variables, x, y, and z. The values for these come from factors relevant to the application. For example, in weather forecasting, this may relate to temperature, wind speed, or pressure. As well as the variables, there are 3 constants, rho, sigma, and beta. The role of these is to create the shape of the attractor and ultimately allow the equations to be useful. Although the values for these can be changed slightly and the equations will still work, they are commonly given the values sigma of 10, rho 28, and beta of 8/3. The crucial part in the equations for creating chaos are the nonlinear terms x, y, and xz. Because of their nonlinearity, they have to be put into a computer program to be solved, and they model chaotic systems. As t, which represents time, also appears in the equations, the chaotic systems are modelled as they change over time.
The Lorenz Attractor is made from a set of chaotic solutions to the Lorenz equations that are considered to be the most chaotic solutions. The attractor itself symbolizes an order within chaos through its shape as it takes the solutions and shows that they do in some way create a pattern. The attractor can be used to represent chaos because of its sensitivity to initial conditions. Chaotic dynamical systems are generally characterized by having a dense collection of points with periodic orbits, being sensitive to initial conditions of the systems and being topologically transitive, vaguely meaning that the neighborhoods of points eventually get flung out to big sets, so they don't necessarily stick together in one localized clump. This means that the Lorenz Attractor is a chaotic dynamical system as it fits the list of characteristics. Therefore, the attractor could be considered as evidence to an order within chaos.
So in order to actually form these equations and form the diagrams which you can see now and a few more which I'll show you in a minute, we used a program called MATLAB. And what MATLAB allows us to do is it allows us to define each equation in the Lorenz equations in order to form a model of the Lorenz Attractor. And you can see a 2D version of it on screen now. However, MATLAB also allows us to define each part of the Lorenz equation separately, so we can plot individual values in order to see how they interact with each other and how they affect the overall model. But because we can define each part of the Lorenz equation separately, we don't just have to plot all three at once in order to form a complete model of the Lorenz Attractor. We can only plot one at a time, but use slightly different starting values in order to see how those starting values are actually affected by the sensitivity to initial conditions when you apply it to real-world values. Here, for example, we've plotted the same equation twice, however, using slightly different starting values each time. And although you might not be able to see it, the two lines are in fact different, and if we zoom in, this difference becomes much clearer. Extending the time over which the Lorenz equations are plotted also makes this difference clearer, as at around the 14-second mark, the two lines diverge quite drastically, very clearly proving that the Lorenz equations do in fact adhere to sensitivity to initial conditions. But regardless of the starting values used, if you plot all three Lorenz equations at once, you will get a complete model of the Lorenz Attractor, which you can see on screen now being viewed from different angles.
There are many examples of chaos. Some are very obviously complex, like weather prediction and stock markets. However, some seem very simple, like a pendulum on the end of another pendulum. Here you can see that. So the blue line shows the path of the second pendulum. At the start they seem very similar, but now as you can see they are very clearly different. These are at very similar angles. And this shows that they are sensitive to initial conditions. Because measuring equipment can never be precise enough to get the initial conditions perfectly right. In weather prediction, the area covered is split into grids. This means that this is smaller for smaller areas because computer power doesn't need to cover such a large area. And this means that for the global model, which is 25 kilometer wide grids, it would miss a weather system that's 10 kilometers in diameter, which could cause major flooding, whereas the UK model of 1.5 kilometers would not.
So, in creating his three differential equations, Edward Lorenz made a fundamental contribution to the mathematics of chaos. By using these equations within the attractor, chaotic systems can be shown to be unpredictable. However, the equations also make it possible to predict the most likely short-term outcomes.
We would like to thank Dr. Bob Bear for setting the question and John for helping us throughout.